Welcome back to CS Connect series. In this video, we are going to learn about a mathematical structure called functions. In the context of mathematics, function is something different from what we have learnt in programming languages. So, set is one such mathematical structure which we have detailedly discussed in this channel. Now, we are getting into another mathematical structure called functions. What are functions? Let's first remind the set elements now. In many instances, we assign to each element of a set a particular element of a second set. Suppose each student in a discrete mathematics class is assigned a letter grade from the set A, B, C, D, F. So let's take two non-empty sets. Let us name it as A and B. We have student 1, student 2, student 3, student 4 and student 5 in set A, and then we have the grades A, B, C, D, F in set B. Now we have a mapping. Student 1 is assigned grade B, student 5 is assigned grade B, student 2 is assigned grade F, student 3 is assigned grade A, student 4 is assigned grade D, and no student has got grade C. This assignment is an example of a function. A function f from A to B is an assignment of exactly one element of B to each element of A. It means when you have set A here and set B here, it should have only one value from B. Say for example, student 1 is assigned only grade B. Student 5 is assigned only grade B. This set B can have any value from set A. That is not an issue. But set A, the first set, should be assigned only one value from the other set. So here we can say the function f maps A to B. If f is a function from A to B, then f can be represented by A to B. A is the domain of f and B is the codomain of f. So when there is a mapping, a domain should contain only one codomain value, but a codomain value can have multiple domain elements. Let's take an element A from set A and let's take element B from set B. This mapping of f is given by f of A. It means when you apply the value A to this particular function, you will get B. This is what they have given as B is equal to f of A. F of A is equal to B if B is the unique element of set B assigned by the function f to the element A of set A. So the unique element should be picked up from the codomain for a particular value or a particular element in the domain. Here B is the image of A and A is the pre-image of B. So let's take the mapping of A and B like this. If this is going to be the image, then this will be the pre-image. So what is B here? It is the image of A. What is A here? It is the pre-image of B. The range or image of F is the set of all images of elements of A. So in this example, what are the mapped values from set B? A is assigned, B is assigned, D is assigned and F is assigned. So this A, B, D, F will alone be called as the range or image of the function. C is not assigned to any of the element from set A. So this will not be a part of the range or this will not be a part of the image. Now let's discuss the same example in the context of domain, codomain and range. Let G be the function that assigns a grade to a student in our discrete mathematics class. The domain of G is the set student 1, student 2, student 3, student 4 and student 5. All the 5 students are the elements of the domain. What is the codomain? It will include all the grades. Whether it is assigned or not, that doesn't matter. You have to include all the grades A, B, C, D, F. Now, what is the range? As I explained before, whatever value in the codomain has been assigned a value from the domain, those elements will alone be taken. So A, B, D, F are taken. Since each grade except C is assigned to some student, we are including only those grades under the range. A function is called real valued if its codomain is a set of real numbers. This part. A function is called integer valued if its codomain is the set of integers. Two real valued functions or two integer valued functions with the same domain can be added as well as multiplied. Let f1 and f2 be functions from a to r. Then f1 plus f2 and f1 into f2 are also functions from a to r defined for all x that belongs to a by f1 plus f2 of x is given by f1 of x plus f2 of x. Then the product f1 into f2 of x is given by f1 of x into f2 of x. So you are applying this particular value to each of the functions. That is what you can see in the right hand side of both the equations. Let f1 and f2 be functions from r to r such that f1 of x is equal to x square, f2 of x is equal to x minus x square. Now we will find f1 plus f2 of x. What we have to do? We have to add both the functions. So it will be x square plus x minus x square. So x square and minus x square will get cancelled and you will have x as the answer for f1 plus f2. What about f1 into f2? X square into x minus x square. So x square into x is x cube. X square into x square is x power 4, and since we have a minus we retain it as it is. So this will be the product of f1 and f2. When f is a function from a to b, the image of a subset of a can also be defined. Let f be a function from a to b and s be the subset of a. The image of s under the function f is the subset of b that consists of the images of the elements of S. So this is nothing but whichever has been mapped from the domain, those values will alone be taken under the image. The image of S is denoted by f of S. So it has to be taken as a set. The shorthand notation can be mentioned in this way. Here f of S denotes a set and not the value of the function f for the set S. So whatever elements are included in the image will be included in f of S set. Let a is equal to a comma b comma c comma d comma e. So let's take it in this way: a, b, c, d, e. This is set capital A. Let b is equal to 1, 2, 3, 4. So we will have 1, 2, 3, 4. F of a is assigned the value 2. F of b is assigned the value 1. F of c is assigned 4. F of d is assigned 1. F of e is also assigned 1. The image of the subset S is equal to B, C, D. So only for these three elements they are asking the image. So this is what they say: S is a subset of A means A is actually the domain of the particular function. So from the domain we are picking a subset. So the domain is A, B, C, D, E. This subset capital S is only B, C, D. So what are the mappings of B, C, D? B is mapping to 1, C is mapping to 4 and D is mapping to 1. So from this, what is the image values possible? 1 and 4. So the image of this particular subset is the set f of s which has the elements 1, 4. Now let's read this line. The image of S under the function is the subset of B that consists of the image of the elements of S. That is, this particular 1, 4 is what they say the subset of B. What is B? 1, 2, 3, 4. Is this a subset? Yes, it's a subset. So the image of this particular capital S will be the subset of B. Whichever element is the image of capital S, that alone will be included. That's why we are including only 1, 4. Now let's take this mapping. Some functions never assign the same value to two different domain elements. We are actually seeing certain properties of functions, we can say, or we can say different kinds of correspondence or different kinds of mappings we can say. So one such mapping is they will never assign the same value to two different domain elements. It means every domain will have different values. A is mapped to 4, B is mapped to 5, C is mapped to 1, D is mapped to 3. It will never assign the same value to two different domain elements. One will not take two different domain elements. At the same time, even if 2 is left out, that is not an issue. A function f is said to be one-to-one or an injunction if and only if f of a is equal to f of b implies that a is equal to b for all a and b in the domain of f. What does this particular line say? It says that only when the value of a is equal to b, we will have the value of f of a is equal to f of b. A function is said to be injective, otherwise in noun form it is injunction. If it is one-to-one, whenever you want to represent one-to-one function, you can call it as injective function. A function f is one-to-one if and only if f of a not equal to f of b whenever a not equal to b. So here they have told in the context of equal to, here they have expressed in the context of not equal to. Expressing f as one-to-one using quantifiers, how can we represent for all a and for all b? F of a is equal to f of b implies a is equal to b. This is one way of expressing it. Otherwise, for all a and for all b, if a is not equal to b, then f of a is not equal to f of b. So read it as we read a conditional statement. If f of a is equal to f of b, then we can say a is equal to b. But here, if a is not equal to b, then we can say f of a is not equal to f of b, where the universe of discourse is the domain of the function. A function f whose domain and codomain are subsets of the set of real numbers is called increasing. Whenever we have f of x less than or equal to f of y, so f of x less than f of y condition is strictly increasing. What about decreasing? When f of x is greater than or equal to f of y, it is decreasing. When f of x is greater than f of y, it is strictly decreasing. So whenever you have only the less than and greater than symbol, we go with the term strictly. Whenever x is less than y and x and y are in the domain of f, at those places we apply these four terms. How can we represent increasing in terms of propositional logic or in terms of quantifiers? For all values of x and for all values of y, if x is less than y as we say here, then f of x is less than or equal to f of y. What about the next one? If x is less than y, then f of x is less than f of y. What about decreasing? If x is less than y, then f of x is greater than or equal to f of y. Here, if x is less than y, then f of x is greater than f of y. A function that is either strictly increasing or strictly decreasing must be one-to-one. So both these functions will be one-to-one. Now let's take another example. Here all the elements are assigned to the codomain and you have two domain elements mapping to the same codomain element. For some functions, the range and the codomain are equal. In the previous example, 2 was never assigned to any function. It means the codomain has 1, 2, 3, 4, 5 and the range has 1, 3, 4, 5. The range is a subset of codomain, but it is not equal. Sometimes we have the possibility of having the range and the codomain to be equal. On seeing this mapping, what you can understand from the codomain? We have the elements 1, 2, 3. What about the range? It is also 1, 2, 3. Every member of the codomain is the image of some element of the domain. A function f from a to b is called onto or a surjection if and only if for every element b that belongs to b, the codomain, there is an element a that belongs to a, the domain, with the function f of a is equal to b. A function f is called surjective if it is onto. A function f is onto if for all y there is a x. F of x is equal to y is what we can take, where the domain for x is the domain of the function and the domain for y is the codomain of the function. It means there is at least one value from the domain that is being mapped to the codomain. The function f is a one-to-one correspondence or a bijection if it is both one-to-one and onto. Such a function is called bijective function. So let's take an example. We have a is equal to 4, b is equal to 1, c is equal to 3 and d is equal to 2. Is the range equal to codomain? Yes, it is equal. So in this case it is onto. Here if you take in this particular example, a and d are mapping to 3. Is such a case happening here? No. Now this can be also taken as one-to-one mapping. So when a mapping is both injective and surjective, you can say it is bijective. Now we will see the different types of correspondences. This is one-to-one as well as onto. Now this is actually one-to-one, but is this onto? No, because the range is not equivalent to codomain. So this is one-to-one but not onto. Let's take the next mapping. It is onto, but is it one-to-one? No. A and D are getting mapped to the same codomain element. So this can be taken as onto but not one-to-one. Suppose that there is a function from a to b. To show that f is injective in the sense it is one-to-one, show that if f of x is equal to f of y for arbitrary x comma y that belongs to set A with x not equal to y, then we can say x is equal to y. To show that f is not injective, find particular elements x comma y that belongs to A such that x is not equal to y and f of x is equal to f of y. To show that f is surjective, this is about onto. Consider an arbitrary element y that belongs to B and find an element x that belongs to A such that f of x is equal to y. How can we say that f is not surjective, that is not onto? Find a particular y from the codomain such that f of x is not equal to y for all x that belongs to A. If none of the domain elements are getting mapped to this particular element from the codomain, at that time we can say it is not surjective. That's why we are marking it is not onto. Now we have another correspondence. We have two mappings here. So this is not one-to-one. We have left one element in the codomain. So range is not equal to codomain. This is not onto also. This is the case where it is neither one-to-one nor onto. Now let's look at this mapping. Can you find something unusual from the examples that we have seen so far? B is mapping to 1. C is mapping to 3. What about A? A is mapping to 2 and A is mapping to 4. What is actually a function? We said domain should map only to one codomain value. But just check, A is a domain element. It is mapping to two codomain value, which is actually not a function at all. So we can say that this is not a function. When you have two mappings from the domain element, you can conclude that it is not a function. Since it sends an element to two different elements, A to 2 and A to 4, we are concluding that this is not a function. So on seeing a particular mapping, you have to check whether it's a function. If it's a function, then check whether it is onto or one-to-one. Sometimes it can satisfy both, sometimes it will not satisfy both. Now we'll get into the inverse functions topic. Let f be a one-to-one correspondence from set A to set B. So this is what we saw in function mapping. This is set A, this is set B. We have an element A in set A and element B in set B. F is an onto function. Every element of B is the image of some element in A. F is a one-to-one function. Every element of B is the image of a unique element of A. So it is both one-to-one and onto. That's why it is given as one-to-one correspondence. A function can be defined from B to A that reverses the correspondence given by F. How can this happen? That is given by inverse function. The inverse function of f is the function that assigns to an element B belonging to B the unique element A in A such that f of A is equal to B. The inverse function of f is denoted by f inverse. Hence, f inverse of B will be equal to A when f of A is equal to B. So, just take f of A is equal to B. When you want to invert, this will be using f inverse of this particular value here. You will be able to get A here. So, just see the mapping. When it is from B to A, it is denoted by f inverse, and f inverse of B is equal to this value A. So, if B is denoted by f of A, then A can be denoted by f inverse of B in case of inverse function. A one-to-one correspondence is called invertible because we can define an inverse of this function. What is inverse of an inverse function? That will be equal to the original function. A function is not invertible if it is not a one-to-one correspondence because the inverse of such a function does not exist. To find whether it is invertible or not, you have to first check whether it has one-to-one correspondence. So, you have to check for two properties, that is one-to-one as well as onto. Now, let's go with an example. Let f be the function from a, b, c to 1, 2, 3 such that f of a is equal to 2, f of b is equal to 3 and f of c is equal to 1. Is f invertible? If it is invertible, what is its inverse? This is going to be the domain. Let's take this to be set A and this is the codomain, this is set B. Is the codomain equal to range? Yes. So, the function is onto. What about one-to-one? A is mapping to 2, B is mapping to 3 and C is mapping to 1. So, we have unique mapping here. So, this is 1 to 1 also. Since we have both these properties to be true, we can say it has a one-to-one correspondence. When a function has one-to-one correspondence, what we can say? We can say it is invertible. So, the first question will have the answer, yes, it is invertible. The function f is invertible because it is a one-to-one correspondence. The inverse of a function, f inverse, reverses the correspondence given by f. How should we reverse? So, let's have f inverse. This 2 will get inside and a will come outside. F inverse of 2 is equal to a. F inverse of 3 is equal to b. F inverse of 1 is equal to c. This is how we will be finding the inverse. Now let's take another example. Let f be the function from R to R with f of x is equal to x square. Is f invertible? So when x is positive, let's take x is equal to 1. X square will be equal to 1 here. When x is equal to 2, we will have x square is equal to 4. What about x is equal to minus 1? We will have x square as 1 again. What about x is equal to minus 2? We will have 4 again in place of x square. Now 1 will be mapping to 1, minus 1 will also be mapping to 1. 2 will be mapping to 4, minus 2 will also be mapping to 4. Do we have one-to-one correspondence? No, the function is onto, but it is not one-to-one. Why? Here, two values in the domain are taking this particular codomain value, which is not one-to-one. Since the function is not one-to-one, it is not one-to-one correspondence, and because of that, we can say f is not invertible. F of minus 2 is equal to f of 2, which is equal to 4. So, f is not 1 to 1. I have given you a small mapping only with minus 2 and plus 2 mapping to 4. If an inverse function were defined, it would have to assign 2 elements to 4. Just reverse this. Now, we will have 1 and 4 in the domain. We will have 1, 2, minus 1, minus 2 in the codomain. 1 will be mapping to 2 values here and 4 will be mapping to 2 values here. What did we see just before some time? This is not a function at all, because domain should have exactly one mapping to a codomain value. When you have 2 values from the domain, that is wrong. If we define an inverse function, we should assign 2 elements to 4 as per this example. If we have 4 here, 2 and minus 2, it should be assigned in this way, which is actually not a function at all. So, we can say f is not invertible. This is the reason why they say one-to-one correspondence will alone give invertible functions. When they don't have one-to-one correspondence, if you try to invert them, you will end up with something that is not a function. If the function f of x is equal to x square is restricted to a function from the set of all non-negative real numbers to the set of all non-negative real numbers, then f is invertible. How is it possible? 1 square will lead to 1, 2 square will lead to 4, 3 square will lead to 9. Is it 1 to 1? Yes, it is 1 to 1. Is it on to? Yes, it is on to. So, we have 1 to 1 correspondence here when we are considering only the positive real numbers to positive real numbers mapping. Just reverse it, 1, 4, 9 here and 1, 2, 3 here. Again we have this mapping only. So, here also it has 1 to 1 correspondence. So, this is an other case that you need to remember, because they might give you different domain context and ask you in which case it is invertible. F of x is equal to x square, which is equal to y. Its inverse is given by f inverse of y. And how will you find the value? It is square root of y. So, if we have f inverse of 4, it is square root of 4, which is equal to 2. If we have f inverse of 9, it is square root of 9, which is equal to 3. So, this mapping is what they have given. Now, let's get into compositions of functions topic. Let G be a function from the set A to the set B, and let F be a function from set B to the set C. So, there are 3 sets that is being involved. Let's look in illustration form. A to B, it is function G, and B to C, it is function F. The composition of functions f and g denoted for all A that belongs to set A by f composite G is defined by f composite G of A is equal to f of G of A. So, this A is present here. Basically, we have to find the value of G of A, and this G of A will be passed as the parameter inside f. So, this becomes f of G of A, ultimately giving the value of f composite G of A. Now, let's see an example. I hope the illustration is actually giving you a clear picture of what this particular statement is saying. Let f and g be the functions from the set of integers to the set of integers defined by f of x is equal to 2x plus 3 and g of x is equal to 3x plus 2. What is the composition of f and g? And what is the composition of g and f? F and g in the sense how you should take, first you have to find for g and then apply for f. What about g composite f of a? This will be in the form of g of f of a. So basically you have to find for f and then apply it to g. So this is composition of g and f. Now let's see the solution. Both the compositions are defined. F composite g of x is given by f of g of x. What is g of x? 3x plus 2 is g of x. Now we have to apply this particular value in place of x in f of x. What is f of x? It is 2x plus 3. What is in the place of x here? X is equal to 3x plus 2. So instead of x we should have 2 into 3x plus 2 plus 3. What is 2 into 3x? It is 6x. 2 into 2 is 4. So this is plus 4 plus 3. So overall you will have 6x plus 7 as the answer. This is the composition of f and g. What about the composition of g and f? Now we have to apply f of x first. So this will be taken as g of, what is f of x value? It is 2x plus 3. So g of x will be 3x plus 2. Now instead of x you have to pass 2x plus 3 plus 2. So what is 3 into 2? It is 6x. 3 into 3 is 9, then 2. So this will give 6x plus 11. Are these two compositions giving the same value? No. The composition of f and g and and f are not equal. The commutative law does not hold for the compositions of function. What is commutative law? When you have A union B, that will be equal to B union A. When you have A intersection B, you will have B intersection A. When the particular sets are interchanged with an operation, the result will be the same. That operation can be union or intersection in terms of set. But here this operation is composition. When you interchange f and g position, they will not result in the same value. It is because the commutative law does not hold for composition of functions. It means they say f composite g is not equal to g composite f. Suppose that f is a one-to-one correspondence from the set A to set B. We have f of A is equal to B. Then the inverse function f inverse exists because it is a one-to-one correspondence and is a one-to-one correspondence from B to A. This can be given by f inverse of B, which is equal to A. Now what is f inverse composition with f? This can be taken as f inverse of f of A. What is f of A? It is B. So what is f inverse of B? It is equal to A. The composition of f inverse and f will be A. What about the composition of f and f inverse? Basically you have to compute f inverse of B, which is equal to A. What is f of A? It is B. Even these two composite functions are giving different values. Now we will get on to the graphs of functions. Let f be a function from the set A to the set B. The graph of the function f is the set of ordered pairs A, B, where A belongs to set A and f of A is equal to B. Where does this B belong to? It belongs to set B. Display the graph of the function f of n is equal to 2n plus 1 from the set of integers to the set of integers. So this is just to illustrate how graph representation is happening. The graph of f is the set of ordered pairs of the form n, 2n plus 1, where n is an integer. So let's start with n is equal to 0. What is 2n plus 1? 2 into 0 plus 1 will give you 1. So the first ordered pair will be 0, 1. Then we have n is equal to 1. So 2 into 1 will give 2. 2 plus 1 will give you 3. So this is 1, 3. Then we have n is equal to 2. 2 into 2 is 4. 4 plus 1 will give you 5. So we have 2, 5. So this is how we will be plotting in a graph. Now we will get on to the next example. Display the graph of the function f of x is equal to x square from the set of integers to the set of integer. Let's include even negative numbers for this case. So let's take the graph of f is the set of ordered pairs of the form x, f of x. This is given by x, x square, where x is an integer. When x is equal to 0, x square is equal to 0. When x is equal to 1, x square is equal to 1. When x is equal to 2, x square is equal to 4. What about x is equal to minus 1? We will have x square is equal to 1. X is equal to minus 2, we have x square is equal to 4. Now we will have 0, 0 from the first. Then we have 1, 1 here and minus 1, 1 here. Then we have 2, 4 and minus 2, 4. So this is 2, 4 and this is minus 2, 4. Then we have 3, 9 and minus 3, 9. So this part is the positive part and this part is the negative part. Now we are moving to flooring and ceiling functions. Actually in mathematical fundamentals video we have already discussed about floor and ceil functions. Now here we are going to discuss the same concept under the context of functions. Let x be a real number. The floor function rounds x down to the closest integer less than or equal to x. And the ceiling function rounds x up to the closest integer greater than or equal to x. So let's take a number 0.5. The floor function rounds down to the closest integer less than or equal to x. So we have 0 here and 1 here. What is less than or equal to x in terms of integer? It is 0. So floor of 0.5 will be 0. What about ceil of 0.5? It will be the closest integer greater than or equal to x. So if this is going to be x, greater than means you will have the value 1 here. Useful properties of the floor and ceiling functions. N is an integer, x is a real number here. Let's take x is equal to 0.5. What is 0.5 in terms of floor? It is 0. So here let's check this condition. N less than or equal to x less than n plus 1. If n is 0, we can have 0 less than or equal to x value is 0.5 less than 0 plus 1 is 1. So this part is actually correct. So we have 4 laws here. Then we have 2a. So from 1c and 1d we can take this particular value. So what is 1c saying? Floor of x is equal to n when x minus 1 is less than n less than or equal to x. So we are starting with x minus 1 less than. Then under ceiling it is given x is less than or equal to n less than x plus 1. So this particular part they are taking from D. In between we are first placing floor that is less than or equal to x, that is less than or equal to ceil. So this is the floor part and this is the ceil part. They have combined 1c and 1d and they have given 2a. Then we have 3a and 3b. This is nothing but applying the negation. This is about adding elements in floor and ceiling functions. So take the floor value of x separately. Consider the real number separately and then take the integer out is what they say. Prove or disprove. Ceiling of x plus y is equal to ceiling of x plus ceiling of y for all real numbers x and y. This statement is actually false. How? A counter example is provided by x is equal to 0.5 and y is equal to 0.5. 1 by 2 is nothing but 0.5. So let's take x plus y now. 1 by 2 plus 1 by 2 will give you 1. That is 0.5 plus 0.5 will give you 1. 1 in ceiling format will give you 1 only. Now let's take x separately. What is ceiling of x? Ceiling of 1 by 2 or ceiling of 0.5 is equal to 1. So x is going to have the value of 1. Similarly, y will also have 1. What is 1 plus 1? It is equal to 2. Now we know this is 1 and this is 2, but it is not equal. So we have disproved this statement and said that both are not equal. We have one more function, the factorial function. This is actually non-negative number. It is denoted by f of n is equal to n factorial. This is the domain and z plus will be the codomain. The value of f of n is equal to n factorial is the product of the first n positive integers. When we have f of n, you have to start with 1 and go till n in multiplication. and we know f of 0 is 0 factorial, which is equal to 1. Say for example, if n is equal to 3, what will be the factorial? 1 into 2 into 3, which is equal to 6. When n is equal to 5, 1 into 2 into 3 into 4 into 5. 5 4s are 20, 23s are 60 into 2, it is 120. So that's what they say in this particular format. This is also a function they have given in terms of mapping here. Now we'll get on to the final topic, partial functions. A program designed to evaluate a function may not produce the correct value of the function for all elements in the domain of this function. It may lead to an infinite loop or an overflow, we can say. A partial function f from a set A to a set B is an assignment to each element A in a subset of A called the domain of definition of f of a unique element B in B. The sets A and B are called the domain and codomain of f respectively. F is undefined for elements in A that are not in the domain of definition of f. When the domain of definition equals A, f is a total function. When you are not able to find values for all the values in the domain but only for few values, that will be partial function. When you are able to find the function mapping for all the values in the set A, that will be a total function. Let's take an example. The function mapping from integer to real number where f of n is equal to root of n is a partial function from z to r, where the domain of definition is the set of non-negative integers. Z means it is integers, but the domain of definition is sticking only to non-negative integers. F is undefined for negative integers. If you have a mapping from z to r, it contains 0, it contains positive numbers, it contains negative numbers. With regard to square root function, they say this square root function is not defined for negative integers. When a part of this particular domain is not defined, you call it to be a partial function. So when do we call total function? When it is possible to calculate a function or calculate a mapping or calculate a value for all the values of z, we call it as total function. When you see practice problems, you can understand this better. Let's get into the practice problems session. Determine whether f is a function from the set of all bit strings to the set of integers. If f of s is the position of a 0 bit in s, this is not a function because there may be no 0 bit in s, or there may be more than one 0 bit in s. So they are asking the position of a 0 bit. Sometimes the bit string can be like this. So in this you don't have any 0 bit. At the same time, when you have more than one 0, which position will you map? You have to map multiple positions here. When you have multiple mapping here, that will definitely not be called as function. Thus, there may be no value or more than one. In either case, this violates the definition of a function since f of s must have a unique value. Now, let's go for f of s is the number of 1 bits in s. We can count the total number of 1 bits and map it to a particular number in the set of integers. So, the bit strings will be the domain here and the set of integers will be the codomain here. This is a function from the set of bit strings to the set of integers. Since the number of 1 bits is always a clearly defined non-negative integer. If the number of 1 bits is going to be 0, it will be mapped to 0. When the number of bits is going to be 1, it will be mapped to 1. The last one, f of s is the smallest integer I such that ith bit of s is 1 and f of s is equal to 0 when s is the empty string, that is the string with no bits. This definition does not tell what to do with a non-empty string consisting of all zeros. It means they said it is the smallest integer such that the ith bit of s is 1. And they have told when s is empty string, the string has no bits. But here they did not say what to do with the 0 strings. In case if the string is going to have 0 completely, they did not say what to do. And if you are going to have 0 1 0 and we'll take the ith bit of s is 1, so the second bit is 1. So we can say for f of 000 it is undefined, so this can be taken for not a function. Next problem, find the domain and range of these functions. The function that assigns to each pair of positive integers the maximum of 2 integers. They are saying each pair. Pair means let's take a comma b. This will be from positive integer and this will be from positive integer. The maximum of these two integers will be the range. So z plus means positive integer. Since we have pair of positive integer, we are using the cross symbol here. Z plus into Z plus will be the domain and range will be only Z plus. Each pair means ordered pair in mathematics. Next one, the function that assigns to each positive integer the number of digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 that do not appear as decimal digits of the integer. What is the domain? We know it's the positive integer. What about the range? Since the decimal representation of an integer has to have at least one digit, at most 9 digits do not appear. It means the decimal value has to start in this way. The number of missing digits could be any number less than 9. We are having the set from 0 to 9. They do not appear as decimal digits of the integer. The function that assigns to a bit string the number of times the block 1 1 appears. So the set of bit strings will be the domain and it is just the number of times the block 11 appears or 1 1 appears. So the range will be the non-negative numbers here or the non-negative integers. The block 11 could appear no times, that is 0, or it could appear any positive number of times. The final one, the function that assigns to a bit string the numerical position of the first one in the string. If the string is going to have 1011 or 1111, we have to take the position of the first one in the string, and that assigns the value 0 to a bit string consists of all zeros. What happens if the bit string doesn't contain any one? Then you have to give the value 0. So they have given both the conditions here. The domain will be the set of bit strings and the range will be from 0 to any number. So it's a non-negative integer. Since the first one can be anywhere in the string, the position can be 1, 2, 3, anything. But if the bit string contains no ones, the value 0 is given by definition here. So we are including the range as 0, 1, 2, 3, which is the non-negative number set. Next problem, determine whether the function integer into integer maps to integer is onto. And onto function is one whose range is the entire codomain. Let's take f of m comma n is equal to m plus n. Given any integer n, we have f of 0 comma n which is equal to n. So the function is onto. When n is present in the domain, n is present in the codomain. So it can be any integer. So this can be taken as the complete set of z. So it is onto. The next one, f of m comma n is equal to m square plus n square. The range contains no negative integers, so the function is not onto. What is z actually? It contains negative integer 0 and positive integer. So when you are squaring up a particular negative number, it will automatically convert to a positive integer. So this particular codomain will have the negative numbers left out. When range is not equal to codomain, it is not onto. What about f comma n is equal to m? Given any integer m, we have f of m comma some number is equal to m. So the function is onto. Any constant can be used for n, but all the values can be mapped is what they say. What about f of m comma n is equal to absolute value of n? The range contains no negative integers. So the function is not onto. Whenever you have a number like -3 here, this symbol will make it positive. So in this case, the negative part of z will never be used in the codomain. So the range will not be equal to codomain. What about E? F of m comma n is equal to m minus n. What is m minus n? The difference. Given any integer m, we have f of m comma 0 which is equal to m. So this will have any value that belongs to the integer part. So the function is onto. Next problem. Determine whether each of these functions is a bijection from R to R. What is bijection? You have to check for one-to-one correspondence. It means you have to check for one-to-one as well as onto properties. One way to determine whether a function is a bijection is to try to construct its inverse. If we try to get the inverse of this particular function, then we can say it has one-to-one correspondence. Let's take the first one. F of x is equal to 2x plus 1. This function is a bijection since it's inverse. So if we take y is equal to 2x plus 1 as the function. Now the inverse function can be taken as g of y. You have to bring everything to this side. So this will go y minus 1. Then you have y minus 1 is equal to 2x. From this what is x? We will have y minus 1 by 2. So you are able to compute a value even from the inverse. So we can say that this is a bijection. Next is f of x is equal to x square plus 1. This is not a bijection just because of this particular power you can understand. The range is the set of real numbers greater than or equal to 1. So from 1 it runs up to infinity. They have given from R to R here. Not all of R. It is not injective either. It is not one-to-one. Even negative numbers will go for the same range value. Next one, f of x is equal to x cube. This function is a bijection since it has an inverse function. How do we find inverse? Let's take y is equal to x cube. The inverse will be taken as y power 1 by 3. By solving y is equal to x cube for x, we can take y power 1 by 3. So there is a possibility to compute inverse function. So we are going with bijection. What about the final one? So let's take x square plus 1 divided by x square plus 2. This is not a bijection. So whenever you have squares involving here, you can always understand one thing. Negative numbers are left as it is. It is not injective. It means it is not one-to-one. Since x and minus x have the same image for all real numbers x. As I told you earlier, negative numbers and positive numbers will map to the same square numbers. It shows that the range is only this one. The positive and the negative number will be mapping to the same square part. So based on this itself, you can say it is not a bijection. Next problem. Let f of x is equal to floor of x square divided by 3. Find f of s. So they have given the set S, the domain part. Now we have to find the values of the function. Now let's take f of minus 2. This will be floor of minus 2 the whole square by 3. This will give a value of 4 by 3. This will be 1 point something. So the value is 1. What about f of minus 1? This will give minus 1 the whole square divided by 3. Which is 1 by 3. This is 0.3 under floor will give 0. What about f of 0? It is 0. What about f of 1? F of 1 will also give 1 by 3 only. So it will come to 0. F of 2 square by 3 will also give 4 by 3. It will come to 1. Then what about f of 3? We have 3 square, that is 9 divided by 3 under floor function. So this is floor of 3 is equal to 3. So what are the possible values of f? We have 1, 0, 3 here. Now the B problem, we have to compute for 0, 1, 2, 3, 4, 5. So we know f of 0 is 0. We know f of 1 is equal to 0. Then f of 2 will be 1. F of 3 will be 3. What about f of 4? We have 4 square, that is 16 divided by 3. This will be 3 5s are 15. It is 5 point something. So in floor we will go with 5. What about f of 5? It is 5 square. 25 by 3. 3 8s are 24. So we will have 8 point something. So 8 point under floor will give you 8. So the result will be 0, 1, 3, 5, 8. What about C? F of 1 is equal to 0. F of 5 is equal to 8. What about F of 7? We have 49 by 3. So 3 16s are 48. So 16 point something in floor will give 16. What about F of 11? So what is 11 square? It is 121 by 3. 40 point something. This will be equal to 40. So the value will be 0, 8, 16 and 40 inside the f of s set. Now we know f of 2 is equal to 1. What about f of 6? 6 square is 36 divided by 3 which is equal to 12. F of 10. 100 divided by 3 is 33 point something. Under floor will give you 33. What about f of 14? It is 14 square. This is 196 divided by 3. So this will be giving 65. So the values are 1, 12, 33 and 65. Next problem. This is regarding composition of function. Find f composition g, g composition f, f plus g and f into g for the functions f and g where f of x is equal to x square plus 1, g of x is equal to x plus 2 are functions from R to R. So let's start with the first composition of f and g. So basically we have to put f of the g value x plus 2. Now we know f of x is equal to x square plus 1. So what we will do here, we will square it up. So what is the expansion? X square plus 2 into 2x which will give 4x plus 2 square is 4 with this particular 1. So x square plus 4x plus 5 will be the answer of composition of f and g. What about composition of g and f? We will have g of x square plus 1. So what is the function? It is just x plus 2. So x square plus 1 plus 2 which will give x square plus 3. This will be the composition of g and f. Now what is f plus g? You have to add both. This will be x square plus 1 from f and x plus 2 from g. So x square plus x plus 1 plus 2 which is equal to 3. Now what is the product? You have to multiply f and g. X square into x will give you x cube. X square into 2 will give you 2x square. X into 1 will give you x and 1 into 2 will give you 2. So this is the final answer. So this is how we will be working with two functions and the composition of functions. Next problem. Show that the function f of x is equal to ax plus b from R to R is invertible, where a and b are constants with a not equal to 0 and find the inverse of f. So we have to prove that this is invertible and then find the inverse of f. Let's solve for the equation y is equal to ax plus b for x. So let's take y is equal to ax plus b. So y minus b is equal to ax. X is equal to y minus b by a. This is what we have got here, which is well defined since a is not equal to 0. Thus the inverse is f inverse of y, which is equal to y minus b by a. F inverse of y should actually give you x and f of x should actually give you y. Now what is in the place of x? We know x is y minus b by a. So we are substituting this particular value. To check for correctness, we must show that the composition of f and f inverse will be equal to y for all y and f inverse and f is equal to x for all x. So we have to find f of f inverse of y. What is f inverse of y? It is y minus b by a. F of y minus b by a. So what is the function actually? A into x plus b. So instead of this x, you have to substitute this particular part. So this will be a into y minus b by a plus b. So a and a will get cancelled, and finally we have y minus b plus b and minus b will get cancelled, and only y will stay. So this is fine. Now we have to find the composition of inverse and f of x. Now what is f inverse of f of x? What is f of x actually? From the question we know it is ax plus b. So what is the equation we have? We have y minus b by a. In the place of y we are having ax plus b. So what we will do is ax plus b minus b by a is what we have to substitute. Plus b and minus b will get cancelled. Then we will have ax by a and a will get cancelled, and finally we will have x. So we have got x here. We have proved both the compositions, and so f is 1 to 1 because f of x1 is equal to f of x2. This implies a of x1 plus b is equal to a of x2 plus b. So from this what we can equate? B and b will go. Then we will have these two equations alone. Then a and a will go. From this we can say x1 is equal to x2. F is on to because f of y minus b by a is equal to y. We have f of x is equal to y. What is the value of x? X is equal to y minus b by a. That is what they have represented in this form. So this is f inverse of y is equal to x. This x is again substituted as y minus b by a. That is what you can find here. So we have proved that it is invertible, and we have found the inverse of the function also. Next problem. Let f be a function from the set A to the set B. Let S be a subset of B. We define the inverse image of S to be the subset of A, whose elements are precisely all pre-images of all elements of S. The inverse image of S by F inverse of S. So F inverse of S is equal to A that belongs to set A, and F of A belongs to set S. So they have given a function with floor of x. Usually they will give you the subset S or the domain A elements, and they will ask you to compute the range or the values or the image for the particular function mapping. But here they have given the image set. Now we are asked to compute the elements of the subset capital S. For what values of S we will get the image as 0 element in the set. This is how we have to interpret the first question. So they have given the image. Using the inverse function we are going to find the subset S that belongs to the domain A. We have to find the set of all numbers whose floor value is 0. Since all numbers from 0 to 1 including 0 but not 1, because when you include 1 the floor value of 1 will not be 0 anymore. From 0.1 till 0.9 everything will be going for 0 in case of floor. Since all numbers from 0 to 1 round down to 0, we conclude G inverse of 0 is equal to 0 less than or equal to x less than 1. That is this interval. So we can include 0, we can go for 0.1 till 0.99 something, it goes on. This particular symbol means it is included. This particular symbol means it is excluded. We have already seen about closed interval and open interval symbols. Now for the second sum they have given -1, 0 and 1. All numbers from -1 to 2. Again we have to not include 2. Will be round down to -1, 0 or 1. If we take -0.5 it will be round down to -1. So any number from -1 to 2 but excluding 2 will be having the floor values of these three numbers. So what is floor of -1.5? Take a scale. This is 0, this is 1, this is -1 and this is -2 and this is 2. What is floor of 0.9? You have to go this way. What is floor of minus 0.5? You have to go this way. What about minus 1.5? You have to go this way. Floor of minus 1.5 will be minus 2. That's why we are starting the range from minus 1 only and not before that. So this will be the answer set here. Now what about the third one? The integer after 0 will be 1. The integer before 1 will be 0. Whatever numbers you get in floor will end up with 0 only, but they have told 0 is not included here. Since g of x is always an integer, there are no values of x such that g of x is strictly between 0 and 1. In this case, we can say the inverse image is empty set. We have from 0.1 to 0.9, we have real numbers. But the floor value of these real numbers should be 0. But here they have given 0 is not included. We know g of x is always an integer, but there is no integer in between 0 and 1. So we can say it's an empty set. Next problem. Prove or disprove each of these statements about the floor and ceiling functions. Let's take A. First they have given floor inside and then they have taken ceiling outside. This will be equivalent to floor of x they have said. So let's pick up a number 0.5. What is 0.5 to the floor value? It is 0. This has become an integer now. Apply ceiling value to it, you will have 0 only. This is actually true. Since floor of x is already an integer, this ceiling will have no meaning. This is actually equivalent to floor of x is equal to floor of x. So this is true only. Only when you have real number you can apply floor or ceil. Already you have applied floor and changed this particular floor of x to an integer. What is the use of applying ceiling to an integer? That's why they say it is true. Next one we have floor of 2 into x is equal to 2 into floor of x whenever x is a real number. Just check 2 into 0.5 will be 1.0 and this will be 2 into 0.5. Here 2 into 0 will give you 0. So they are not equal actually. This is false. One counter example is x is equal to 1 by 2. So let's take 2 into 1 by 2. So we have 1 here in LHS. What about the RHS? We have 2 into floor of 1 by 2. This is 2 into 0 which is equal to 0. This is RHS. I have just told the same example using 0.5 and 0.5 is nothing but 1 by 2 in fraction. Now let's get into C. We have ceiling x, ceiling y minus ceiling x plus y is equal to 0 or 1. This is true. If x or y is an integer, then by property 4b, ceiling of x plus n will be ceiling of x plus n. So the difference is 0 here. If neither x nor y is an integer, then x is equal to n plus epsilon and y is equal to m plus del, where n and m are integers and these two symbols are positive real numbers that are less than 1. So why have they mentioned in this way? If they say it is 0.5, then n will have the value 0, this 0.5 will be sticking to epsilon. If they say 0.7, 0 will be sticking to this m, 0.7 will be sticking to this del symbol. So these two are real numbers they have told, that is less than 1 for the point part, and these are the integer part number. Then we have m plus n is less than x plus y less than m plus n plus 2. Let's take n is equal to 1, m is equal to 1, epsilon is equal to 0.3, del is equal to 0.4. Now what is x? 1.3 and what is y? It is 1.4. Now what is m plus n? It is 1 plus 1 which is equal to 2. What is x plus y? It is 2.7. What is m plus n plus 2? It is 2 plus 2 which is equal to 4. From this we can say ceiling of x plus y is either m plus n plus 1 or m plus n plus 2. So maximum the value is 4 here. So x plus y's ceiling value can be m plus n plus 1. So in this case it is 2 plus 1 which is equal to 3, or m plus n plus 2 which is equal to 4. So the ceiling value can be either this one or this one is what they are trying to say. This is 3 and this is 4. Therefore the given expression is either n plus 1 plus m plus 1. So instead of x we are going with n plus 1, and instead of y we are going with m plus 1, minus we are taking this particular equation now. This is n plus 1 plus m plus 1. Minus should be applied inside. So this is minus m minus n minus 1. M and minus m will get cancelled. N and minus n will get cancelled. 1 and minus 1 will get cancelled. Overall you will have only 1 here. What about if x plus y is taken as m plus n plus 2? In that case we will have n plus 1 plus m plus 1. Then here it will be minus m minus n and minus 2. Here m and minus m will get cancelled. N and minus n will get cancelled. 1 plus 1 will give you 2. So 2 and minus 2 will get cancelled. So you will have only 0 as the answer. Now what are the two possibilities? It will either be 1 or 0 is what they say. So whenever x and y are real numbers, only two values are possible. So we are sticking to true. Now let's go for D. We have the product now. X into y under ceiling is equal to ceiling of x and ceiling of y. Is this true? No. Just take x as 1 by 4 and y as 3. This is 3 by 4. This is 0.75. Ceiling of 0.75 will be equal to 1. This is the LHS. Now what about the RHS? This is 0.25, which will give you 1, and y is equal to 3. So 3 ceiling will be 3 again. What is 1 into 3? We have 3. 3 is in RHS. Are they equal? No. So we can say this is false. Now the final one. X divided by 2 is equal to x plus 1 by 2 for all real numbers x. The LHS is having ceiling function and the RHS is having floor function. This is false, and they have given x is equal to 1 by 2 is a counter example. Let's check. Ceiling of 1 by 2 by 2 will give 1 by 4. What is 1 by 4? It is 0.25. This will be equal to 1, and this is the LHS part. What about the RHS? We have 1 by 2 plus 1 by 2. So 1 by 2 plus 1 will give you 3 by 2 by 2. This will be 3 by 4. What is 3 by 4? It is 0.75. What have they applied here? Floor function. What is floor of 0.7? It is 0. This is the RHS. Are they equal? No. So we can say it is false. Next problem and the final problem. For each of these partial functions, determine its domain, codomain, domain of definition, set of values for which it is undefined. Also determine whether it is a total function. When you find the domain and domain of definition, when they are equal, it's a total function. But in case if you are able to find values for which it is undefined, in that stage itself you have to understand it is not a total function but it's a partial function. Wherever you have undefined values, that will end up with partial function. If there is no undefined values, then it is a total function, and in this case the domain will be equal to the domain of definition definitely. Let's get on to the first function. Integers to real numbers, f of n is equal to 1 by n. So what is the domain? Set of integers. So it is z. What is the codomain? It is real number. It is r. So what is the domain of definition? 1 by n. Do we have something called 1 by 0? No. So domain of definition will exclude 0. So the set of non-zero integers can be placed here. So it can be either positive or negative. That does not matter. But 0 should be excluded. So for what values f is undefined? It is not defined for the element 0. So this can also be taken as z minus 0 here. You can also represent it in this way. Once you have some undefined value here, is this a total function? No, it's a partial function. Whenever we say not a total function, that comes under partial function. The next question. Z maps to Z. So what is the domain? It is Z. What is the codomain? It is Z again. What is the function now? It is n divided by 2, the ceiling value. 0 by 2 will give you 0. Then 1 by 2 will give you 1. Substitute 0, positive, negative integers in this function and check. The domain of definition will have Z again. So the domain and the domain of definition are same here. Which values are undefined? There are no values. This is actually empty set stating that no values are undefined. So this is a total function. Let's go to C. The domain is Z into Z because it is given in the form of ordered pair because we have two values here. What about the codomain? It is Q, rational number. The domain of definition. This particular n value should not be equal to 0. Even when you want to define rational numbers under P by Q, there will be a condition stating Q is not equal to 0. So since n is given an exception, the first number in the ordered pair can be complete Z, but the second number in this particular ordered pair should exclude 0. So there is an exception here. So what is undefined? This particular part is undefined here. So when there is a pair called m comma n, m belongs to this Z and n belongs to 0, there is no definition. Because in rational number, we have q not equal to 0. That is, denominator is not equal to 0. M comma 0 is undefined. So in this case, we can say this is not a total function. Let's go for D. The domain is Z into Z, ordered pair. The codomain is Z. The product of two integers is again integer. There is no difference between domain and domain of definition. Are there any undefined values? No, it's empty. So this is a total function. Now let's go for E. Now let's go for the domain. It is ordered pair Z into Z. Then we have the codomain Z here. Now the domain of definition. It is given as m minus n if m greater than n. So there is a condition specified here. So this will be the domain of definition for the ordered pair m comma n. Is there anything undefined? They have given it for m greater than n. What about m equals n or what about m is less than n? These two cases are not defined. So this can be taken as the set of values for which f is undefined. M less than or equal to n. So we have combined both these conditions and kept here. So when you have an entry for undefined value, what is it? It is not a total function. So this function mapping is restricted to m greater than n and it is left undefined for m less than or equal to n. So understand, whenever you have undefined value for a function domain set and the domain of definition differs from the domain, you automatically conclude that it's a partial function and not a total function. When the domain and domain of definition are same, at that time you can say it's a total function. And in those cases, the set of values for which the function is undefined will be empty. With this, we are completing this video. I'll meet you in the next video. Thank you, viewers.